When we think about trajectories of a system, or when we talk about a solution starting from some given initial condition for a given system, we implicitly assume, or we take for granted, that such solution exists, okay, always, and it's always unique. Moreover, we further assume that it exists forever, for all future times. Okay. Now, all those things, all those properties, it's true they come for free for linear systems. Okay, for linear systems, therefore we don't have to worry about such issues. But such issues do exist for the general case, for the general nonlinear differential equation. So in this lecture, we will briefly talk about those issues, namely, well, in part, mainly existence and uniqueness. Okay, and we'll see some sufficient conditions that guarantee the existence and uniqueness of solutions for a given differential equation. And moreover, we will mention certain phenomena that doesn't appear, that doesn't happen to linear systems, but can be observed for certain nonlinear systems. One of those phenomena is the fact, for instance, that for a linear system, if the solution, a solution, is converging to some point, let's say an equilibrium point, let's suppose that it's converging to the origin, that convergence even is exponential. It has to be exponential, and even if it's quite fast, okay, the solution never gets to the origin, okay, to the equilibrium point. Infinite, it gets closer and closer and closer, and it gets closer exponentially fast, but it never really reaches the origin, okay? Or it reaches the origin at time t equals infinity, okay? Another way to put that. With certain nonlinear systems, the equilibrium point can be reached in finite time, let's say in 1 second, exactly reached in 1 second. Okay? And we'll also talk about things like that. Okay, so therefore the main concern, our main concern in this lecture is the properties of certain important properties of solutions. Therefore, we begin by what we mean by a solution. Even though we know what it is, it's always good to be precise. Okay. Well, usually good to be precise. So by a solution, we mean the following: a continuous function x, let's call it x, defined in an interval t0 to t1. Okay, t1 is larger than t0, it could be infinity sometimes, and is said to be a solution of the system that's described by the state equation x dot equals f of tx. T is time, x is our state, and we consider the general case we are in Rn, okay, or perhaps a subset of Rn. But it's okay to consider that the state resides in complete n-dimensional space. If x dot t exists, okay, so this derivative with respect to time exists, and satisfies d dt xt, okay, that is x dot equals f of t x of t. Okay. And this equation should hold for all t0 to t1. And then this function defined in that interval, which is a mapping from this interval to Rn, is said to be a function. A function is said to be a solution of the system, a solution that's defined in that interval t0 to t1. Okay. Now let's ask the first important question. existence. Okay. Given a system and the initial condition from which we are to start, when does a solution exist? Okay. The answer, at least for linear time invariant systems, is that it always exists. Okay. But for general case, we have to be careful. Here is a sufficient condition for the existence, and it's very simple to keep in mind. The sufficient condition for existence of a solution is that f, the right hand side, is a continuous function. Okay. Here is a sufficient condition. If f t of x, our right hand side, which we consider general case and is the time varying case, is continuous, with respect to both of its arguments, t and x, its arguments tx, then a solution x t0 t1 and exists where t1 is some number larger than t0. So at least for some t1, the solution defined in this interval exists. Okay. For some interval. And then, how about uniqueness? Okay. Suppose that we have a system, the right hand side is continuous, so automatically we know that the solution exists. Okay. That's our initial condition, and then the right hand side is continuous, therefore we know that there will be, at least, not perhaps for all times, but for some time, there will be some solution starting from the initial condition, x of t. Now, for linear systems, this always exists and it's unique, okay? For linear time invariant systems, and it goes on forever. Now, for nonlinear systems, it doesn't have to be unique. That is, here we have x of t. Okay, that satisfies the definition of solution, but it could be that starting from the same initial condition, from the same initial time, we could find something else. Let's call it x tilde t. Okay, so both satisfy this definition of solution. Perhaps you had a family of solutions, okay, all starting from the same initial condition. Okay, and now for usually that's something that we want to know, or we don't want, if there's something that we can design within our system. So it's good to know that when such thing happens or when it doesn't happen. Okay. And for that we have the following sufficient condition. So next step is uniqueness. Can x dot f tx have multiple solutions? Okay. By multiple solutions, we mean multiple solutions all are starting from the same initial condition. Okay. Now, it turns out that you can generate such systems, okay, that have multiple solutions, and it even turns out that they may have very simple right-hand sides. Okay. Now we'll give an example so that we'll be convinced that the solutions are not always unique. The answer therefore is yes, okay, to that uniqueness question. Consider x dot equals x cube root. Okay, this is a first order system with the initial condition x equals 0. So we have a scalar system starting from the origin. Now here is clearly one solution is that it's an equilibrium point. Okay, therefore one solution is that x of t equals 0 for all future times. Okay, so that's the trivial solution. Solution 1, x of t equals to 0 for all times. Okay, so this triple bar means, or equivalent sign means, x of t is identically equal to 0. That means it's 0 for all times. Okay, so that's notation that some authors use. But that's not the only solution. Consider the other candidate. X of t equals 2t over 3 and raised to the power 1.5. So this is another solution candidate. Now let's see whether it satisfies the definition of a solution. It should satisfy the initial condition constraint. Okay, at t equals 0 it must be 0, which it does. Plug in t equals 0 and x of 0 becomes 0. How about the differential equation constraint? So let's see whether it satisfies that. We have d over dt, x of t, and x of t is the candidate here. So let's differentiate with respect to time. So we have 3 over 2, 2t over 3, 1/2 times 2 over 3. This and that, they will cancel, and we have 2t over 3. Then we take the square root, and that, taking the square root, can be written as follows. That equals 2t over 3, 3 over 2, and then you take the cube root. Okay, 1/3. Okay, we wrote this 1/2 by first taking the 1.5 power and then taking the 1/3 power. Okay. And this is no other than our solution candidate, which was 2t over 3 raised to the power 3 over 2. Then you take the cube root of it. Okay, therefore, x dot equals x raised to the power 1/3. The differential equation constraint is also satisfied. And then, even though this guy starts at 0, as time goes on, it increases. That means this and that, there are different solutions. Okay. So for this differential equation, starting from that initial condition, there are more than one solution. In fact, we can generate more solutions. Solution 3, x of t equals minus 2t over 3, 3 over 2, and so on. Now, how do we rule out this multiplicity, or when can we be sure that the solution will be unique? For that, the most general sufficient condition is the Lipschitz continuity condition. Okay, here is a sufficient condition for uniqueness of solutions is so-called Lipschitz continuity condition. It's only a sufficient condition, okay? So that condition may not be satisfied, and still solutions may be unique. But whenever it is satisfied, then we can be sure that the solutions will be unique. Okay. So here is the theorem. Let t of x, our right hand side, be piecewise continuous with respect to time, or this first argument. With respect to its first argument, t and piecewise continuous means that on any finite interval, there are finite many discontinuous points. So that's what we mean by piecewise continuous. And satisfy the Lipschitz condition. Okay. Which is the norm of f t of x minus f t of y. Okay, so this norm of this difference can be bounded by some constant times the norm of the difference of x and y for some constant L greater than 0. Constant. For all x and y that belongs to set z in Rn and z minus x0 less than or equal to r. Now that x0 is the initial state from which we're investigating whether the solutions stemming from that initial condition are unique or not. Okay, for all xy that belongs to a ball, okay, centered at x0 and with radius r. And what's r? R is just some arbitrary positive number. Okay, and for all t in t0, t1. Okay, so this inequality should hold for all t, okay, in this interval, t0 to t1. t0 is our initial time and t1 is something that's a little bit ahead of t0. Then there exists a positive number, delta, such that equation x that equals f of tx, okay, our system description with initial condition x t0 equals x0 has a unique solution. At least for some time, starting from t0 for some finite length of interval, t0 and t0 plus delta. Okay. Now here is a nice exercise that combines this sufficient condition with this example where we have multiple solutions. Let me write it down for you, exercise. Show that. System x that equals x on third fails to satisfy the Lipschitz condition. Now, that's a quite simple example. It's first order, it's scalar, and also the right hand side doesn't depend on t, so it's extra easy to check this condition on that system. And this condition, in that case, right hand side, forget about t, f of x minus f of y, norm is bounded by some constant times the difference x and y. So we have therefore a linear, in a sense, inequality between the norm of the difference of the right hand side and the norm of the difference of the state. Okay? And if this is never satisfied for no L, so that means we're talking about a slope that's arbitrarily large. In fact, the slope that's infinity. And then in this case, if you look at this right hand side, that function x raised to the power 1/3 at the origin, then even though it's continuous, it has a very aggressive slope, so aggressive that this condition can never be satisfied, no matter how large of an L you choose. Okay. Therefore, this condition cannot be satisfied because it's a sufficient condition. If we could satisfy that condition with some L, then we had to have multiple. We had that unique solution, but we don't have a unique solution. Okay, we have multiple solutions. Therefore, that condition must fail. Okay, so in this exercise, you're asked to do that in a bit more rigorous way. Okay, now here's another way to look at it, and there's another nice exercise that follows. Exercise. Consider the system x that equals f of x with origin being an equilibrium point. The solution x is known to satisfy, let's say, these two things. First of all, solution, okay, it's defined for, let's say, for all time, for the sake of simplicity, and we start from initial time 0, and we can take the initial time to be 0 without loss of generality, because the system is time invariant. Okay, so at 0, we're not at this equilibrium point. Okay, so at 0, we're at time 0, we're not at the origin, but after a while, x at some time, capital T, we are at that equilibrium point. And T is not infinity, it's some finite future time. Or some finite future time, capital T. Show that F cannot or does not satisfy the Lipschitz condition. Okay. And here's a nice hint, or that gives one a nice way to look at the thing from the uniqueness point of view, which is consider solution of x that equals minus f of x. Okay. Now, whenever you put a minus sign in front of your right hand side, you obtain a new system, and that new system is such that you basically just change the direction of time by putting a minus 1 in front of it. That is, if this is a solution, okay, in that direction for your system, then rewind the clock back. This is a solution for the reverse system or for the negative system. Okay, and using that very simple fact, you're asked to show that whenever you have a solution satisfying this condition, where 0 is an equilibrium point, or the origin is an equilibrium point, then you cannot have Lipschitz condition. So somehow you have to introduce non-uniqueness, or find a non-unique, or generate a non-unique solution for this system given such properties, and then from non-uniqueness you will reach the conclusion that the Lipschitz condition cannot be satisfied. Okay. Now, a linear system, an unstable linear system, let's say, may display solutions whose norms grow unbounded. In fact, they can grow unbounded exponentially and quite aggressively too. Okay. So the norm becomes larger and larger. Okay, and it tends to go to infinity. But it never reaches infinity. Okay, in finite time. That's not possible for a linear system. And due to that, solutions for linear system exist for all future times. But for nonlinear systems, the increase could be so aggressive that you reach infinity, the solutions reach infinity in finite time. Let's say in 2 seconds, you hit the ceiling, okay? Ceiling being infinity. And that means once you hit infinity, everything becomes meaningless. Beyond that time, let's say you reach infinity at 3rd second, let's say. Beyond that time, you cannot talk about the solution, because once you're infinity, then you're out of, I don't know, consideration. And the solution, therefore, exists only for finite interval. Okay? So that's, for that phenomenon is called finite escape time. So let's give an example to that. Finite escape time. Just to see that very bizarre things can happen in nonlinear systems, things that we cannot hope to see in linear systems. And one of those phenomena is finite escape time. Consider, again, the example is very simple, very in first order. Consider x equals minus x squared. Okay. Consider this right hand side. Okay, with x0 equals minus 1, starting from that initial condition. Okay, and okay, so the right hand side is continuous, therefore solution exists, and also it's Lipschitz. Okay, therefore solution is unique whenever it exists, throughout the time that it exists. But it doesn't exist for all times. Why? Because we can actually figure out, well, not because, but we can see that because we can actually write down explicitly the solution. We can solve that differential equation even if it's nonlinear. And the solution is this. The solution is unique. X 0, 1 to R with x of t equals t minus 1. Okay? At t equals 0, plug in t equals 0, you have 1 over minus 1. So you have minus 1 initial constraint, and it's also easy to check that this candidate satisfies the differential equation. Therefore, it's the solution to that differential equation. And now, what happens with that solution is that we're starting at minus 1, and then at that point t equals 0. And then what happens is t becomes larger and larger. So as t becomes larger and larger, this becomes what? Smaller and smaller, okay, but still negative, okay? Let's say t equals 1/2, and this is minus 1/2, 1 over minus 1/2, it is minus 2. And then the difference becomes minus 1/3, and then we are at minus 3. Then the difference becomes minus 1/5, and so on. So this increases to toward minus infinity. Okay? And it does that in a finite amount of time because you can make this guy, the denominator, arbitrarily small within this interval, finite time. You can just choose some t that's very, very close to 1, then this difference will be very tiny. 1 over that very tiny number will be very large. And all I said can be nicely put or in this picture or seen in this picture. 0 x of t, t. Okay, so this is the initial condition. We start at minus 1. And what happens is, as you approach time t equals 1, x of t, the norm of x of t increases unbounded. Okay. And then at t equals 1, everything becomes infinity. Okay. Hence, and once something becomes infinity, there's no point to talk further. That means solutions exist only between 0 and 1. Solution is undefined or doesn't exist for t greater than or equal to 1. Note that as we approach the second one, t equals to 1, we have x of t equal to infinity. Okay. Now this phenomenon, or such behavior, is called finite escape time. So it escapes to, in a sense, infinity. Now, one way to rule out finite escape times is strengthening the Lipschitz condition into the following, into the so-called global Lipschitz condition. Here is our last theorem. Let f tx be piecewise continuous. T and satisfy ftx minus fty x minus y. Okay, so this is our Lipschitz condition that we have already talked about. For some constant, positive constant, for all xy in Rn. Now previously we wanted the condition had to be valid only in some neighborhood of the initial condition. Now we require that to avoid finite escape times. Now we require that it's true for all, for the entire space xy in Rn, and for all t in t0, t1. Okay. Then the state equation x ft of x, our system, that is, with initial condition x t0 equals x0 for some x0 have a unique solution over the entire candidate interval t0 to t1. Okay. If this is true for all times, let's say, then the solution extends for all times. Okay. And the last exercise that has to do with the absence of, or the guaranteeing absence of, finite escape times is the following exercise. Consider the linear system x that equals a tx. Okay, so that's clearly linear time varying system where a is a continuous function of time, by which we mean, so this will have n square entries, and all those entries are, all those scalar functions are continuous. Show that for all initial state starting from an arbitrary any initial time t0, a unique solution x t0, okay, that extends to infinity and with x t0 equals x0, that's where we start from, exists. Okay. Now, you cannot directly apply this theorem to solve that exercise because a of t is function of time, and now we're interested in solutions for all future times, and that means if you want to apply this theorem directly, that would require being able to find a constant L that would bound the norm of this matrix A of t for all future times. Okay, but we're not told anything about boundedness of the entries. We're only told that the entries are continuous. So therefore, it requires a little bit work. So what you're going to do is you're going to apply this theorem in a piece-by-piece or step-by-step manner. And all those steps, if you put one after the other, will take you in the solution to the infinity. Okay, you can do that, and it's a nice exercise to apply this theorem.